2 of the Unit 2 of Financial Modeling course. Session 2 focuses on the estimation of linear regression model. By the end of this session, you should be able to identify common estimation techniques of linear regression. Also, you should be able to distinguish between population and sample functions. And finally, you should be able to calculate error sum of squared of least square regression. Estimation techniques plays an important role in regression analysis and financial modeling. We earlier said that there are steps in building financial model or in estimating models. The first was that you should be able to identify a theory. So we are saying that after establishing a sound finance or economic theory and obtaining the right quality of data, that's data quality, the logical question will now be how we should estimate the regression model or the regression analysis. So the most common method used to fit a line to the data is known as the ordinary least square. That is, we are looking at a line that can measure the average of all these data sets, or that represent the average of all the data sets. So there are alternative methods which includes the method of movement or the generalized method of movement by Hansen and the method of maximum likelihood. But in this session, our focus will be on the OLS, that is the ordinary least square, which focus on mounting or plotting a line which captures the average behavior of all the data sets or all the variables that we are targeting or that we are estimating. OLS, or the ordinary least square, can simply be expressed as in equation 2.3, where we are focusing on estimating the error term, that is the disturbance term, the factor which affects the regressant, which mostly in our equation is not being captured, or we are not able to capture due to other factors that we have earlier mentioned. The OLS method for estimating the coefficient aims at minimizing the sum of squared errors. So we are hoping to minimize the error term, that is the effect of the error term in the estimation of our model. So by minimization of the sum of squared errors, we are simply looking at how best we are able to reduce the chance of we making an error in our estimation to the barest minimum. And by doing so, our aim will be to get a beta coefficient that will make the error sum of squared as small as possible. And this is captured in the equation 2.4. In minimizing the error sum of squared, we are required to take the partial differential calculus, where each coefficient is written as beta. So here we are assuming the slope coefficient, which is the beta 1, becomes or is equal to the partial derivative, that is this symbol represents the partial derivative of the regressant, that is the dependent variable, all over the partial derivative or the partial differentiation of the regressor, which is the explanatory variable. Sometimes it might not be the case that we will have only one independent variable. We could have multiple independent variables. Therefore, it could be from I up to maybe k. So k represents the last term or the last explanatory variable that we are going to adopt in estimating our beta coefficient. So we should also understand that we cannot calculate this manually. So there are statistical packages that will help us do the estimations in arriving at the beta coefficient. So but after the estimation, we are no longer going to use the capital beta component, but we are now going to represent this beta with small b, which indicate that this is an estimate. So our equation will now be represented unlike that of equation 2.1 and 2.2. We are no longer going to use that equation, but now we are going to represent them with small letters. Here, with the y hat, this symbol, the hat on the y, which is a regressant, represent or indicate that we are now estimating these parameters and no longer using the population as we saw in equation 2.1 and 2.2. So this equation, that is equation 2.7, is similar to that of equation 2.1, and equation 2.8 is similar to equation 2.8, only that here no longer using the population, we are now using estimate other than the population. The 2.1 depicts the ordinary least square plot where we have the x-axis and the y-axis. This is the y-axis and this is the x-axis. Assuming the x-axis represents the predictor, which is the independent variable, while the y-axis represents the predicting of the dependent variable. What we are simply saying is that we want a line, which is this line, or a value which can represent the average behavior of these variables. In simple terms, we simply want an average value or a predictor variable, x, this variable, x, which which can explain the movement in the predicting variable y. So our focus is to fit a model. So we are hoping to we seek to fit a model in such a way that the average value that we will select can capture the average random behavior of this data set. So we are assuming that on this model there will be data set that will be plotted. If we plot, or if we are to plot our data set, we are hoping that all these data sets will be found around this line of fit. So this fitted line, we are hoping that our data set will be found around this line. So assuming that let's hope that these variables are, or this predictive variable and the predictor variable are a member of a family. What we are simply saying is that it's like selecting a single member of family to represent the whole family. So we are saying that this member should at least possess all the relevant attributes of this family plus any other unique quality of their own. But you also agree that this behavior of a single family member will in a way possess its own limitation. In this sense, the actual behavior pattern of the family will be represented by the y, by this y. So the population of the actual will be represented by the y, which we call the population in the case of the predictive variable, while the selected behavior from the random family member will be given by that is the average, which is the y hat. So we have the y, which is the population, and we have the y hat, which is the estimate or the average, which in this case is also serves as our estimate. So what we are simply saying is the difference between the value y, which is the true value, and the estimate, or the estimated value, is what we refer to as the error term. So this error term, we are simply saying that the difference between y and the y hat is simple, or the y bar. This is the y, and the y is the population, and the y bar is the average, or let's say the average. And here we are, the y is still the population, and this one, the y hat, is the estimate. And then the difference between the actual and the estimate is what we refer to as the error term, or the error term. So our focus is to choose an estimate that will have the least error term as possible. Our hope, or our focus, is to reduce or to estimate a model to the extent that this error term will be at the barest minimum. So in summary, the variation of the regression, which is the y variable around its mean, can be decomposed into two. Like it can be decomposed into two. That's the difference between the population and the estimate, and also the difference between the population and the average value. So the difference between any of these, that is the difference between the population and the average, which is the y bar, is simply the average, which is the average of the predictor variable, the predicting variable, and the y hat is the estimate. The difference between any of these is what we refer to as the error term, and it's also possible that it's like choosing a member of family to represent the entire family. What we are simply saying is that there is a possibility that the unique attributes of the family as a whole cannot be possessed by just a single person. So there is a possibility of there being a limitation of some variation. So it is this variation that we refer to as the error term. In summary, we've been able to identify common estimation techniques of linear regression, distinguish between population and sample function, and calculated error sum of squared of least square regression. Thank you.